Physics for Philosophers, An Introduction, by Tomasz Begich. Chapter 1, Section 1. Ancient Astronomy. Astronomical phenomena have attracted attention of mankind since time immemorial. Sunrises and sunsets, the annual variability of the sun's position in the sky, the phases of the moon, constellations, and their revolution in the night sky, all this stimulated people's imagination and made them ponder. Difficult to predict eclipses of the moon and the sun, or the sporadic appearances of comets, caused terror, but also piqued curiosity. The religious significance of celestial phenomena is well known, from the ritual celebration of the solstices in megalithic buildings of the Stone Age to the Egyptian pyramids and their alignments with the constellations. Gradually, however, the mythological and anthropomorphic approach to astronomical phenomena began to be replaced by naturalistic considerations. Bold hypotheses have been developed about the nature of the bodies observed in the sky, their relationships with each other, and the hidden mechanisms responsible for their behavior. In this section, we will learn the basics of the most advanced system of ancient astronomy. This title undoubtedly belongs to the geocentric system of Claudius Ptolemy, a Greek scholar from Alexandria, who lived and worked in the 2nd century AD. We will trace the path that ancient astronomers had to traverse, from singular observations and facts to the theoretical hypotheses and generalizations of the Ptolemaic model. We will begin our journey in time to the inception of astronomy by presenting the basic empirical data that ancient stargazers had at their disposal. A cursory observation of the night sky teaches us that the celestial sphere is constantly rotating around a certain point in the sky occupied by the North Star, also known as Polaris. All objects in the sky visible to the naked eye, the stars, the sun and the moon, as well as ephemera such as occasional comets, participate in this movement. Moreover, ancient travelers observed that the elevation of Polaris changes depending on the position of the observer. The further north we go, the higher Polaris appears in the sky. On the other hand, traveling south, towards the equator, results in lowering the apparent altitude of the North Star until it meets the horizon. Another important fact, well known to the observers, was the existence of a different type of motion for some celestial bodies beyond the diurnal, i.e. daily, rotation of the entire sphere. For now, we will skip the movements of the moon, which, along with the change in its observed shape, the phases of the moon, posed a great challenge. In the case of the sun, on the other hand, it can be seen that it makes a slow motion against the background of stars in the opposite direction to the direction of rotation of the entire celestial sphere. In other words, the sun retreats relative to fixed stars, completing a full cycle during one calendar year, so the solar day is about 1/365 day longer than the sidereal, i.e. based on the star's day. By tracing the path of the sun's year-round motion in the sky, we get a circle called the ecliptic. This circle is located in a belt dubbed the zodiac, known for the fact that it is divided into 12 constellations, from the constellations of Aries, Taurus, Gemini to Pisces. The sun resides in each constellation for 1 month. The plane of the ecliptic is inclined with respect to the celestial equator, i.e. the large circle perpendicular to the axis of diurnal rotation. This fact is of paramount importance for life on Earth, since its consequence is the annual variability of the point of the highest daily position of the sun from the highest in the summer months to the lowest during the winter. Determining the key points of the equinoxes and solstices for the annual motion of the sun was of great significance from a practical and ritual point of view. However, far more crucial for the development of astronomy was the behavior of a special category of objects in the night sky, the so-called wandering stars, that is planets. The planets are characterized by a significant brightness compared to the rest of the stars. The ancients distinguished 5 planets named after Roman gods: Mercury, Venus, Mars, Jupiter and Saturn. Their characteristic feature is that, like the sun, they change their position in relation to the fixed stars. Each planet makes a slow motion in the zodiac belt in the opposite direction to the daily rotation. However, the speeds of this movement vary from planet to planet. Mercury and Venus are the fastest, Mars is slower, and Jupiter and Saturn are the slowest. However, the complexity of planetary motion does not end there. First, the migration of individual planets against the rest of the stars is not uniform, as in the case of the Sun. At certain times, the planets move faster, and at other times they slow down. Moreover, these slow changes in pace are compounded by rapid changes in both speed and direction of movement. Careful sky observers have noticed that each planet goes through a period of slowing down, stopping, and going backwards, after which it returns to normal motion. In other words, the planets draw small loops in the sky. Such a movement is called today retrograde. It is characteristic that Mars, Jupiter, and Saturn, called the outer planets for reasons we will soon see, perform retrograde motions no more than once a year, while the inner planets Mercury and Venus are in retrograde several times a year. To these observational facts, let us add that the inner planets always stay close to the Sun, they never stray too far from it, as if they were tied to it, they appear from one side of the Sun and then from the other. The outer planets, on the other hand, move freely, from time to time being in the so-called opposition to the Sun, exactly on the other side of the celestial sphere. Finally, let us mention the well-known and easily noticeable fact that the brightness of the planets, especially the outer ones, varies greatly in time. In some periods, for example Jupiter is extremely bright, and in others its light seems to dim. This, of course, stands in stark contrast to other stars whose brightness remains the same. As you can see, the ancients collected a lot of empirical material regarding the behavior of individual celestial bodies. The next step should be to put all these various facts into a coherent whole. Such a whole, called a theory or model, should provide us with a uniform explanation of the individual observable regularities. The question why is one of the fundamental questions that people have asked since the dawn of time. It is not easy to determine what kind of requirements we should impose on scientific explanations. Instead of formulating a ready-made philosophical concept of explanation in science, we will simply look at how explanations functioned in astronomy, and later also in physics. In any case, we can assume that the explanations of individual unrelated facts should in a sense, go beyond a mere collection of these facts, they should contain some added value. This added value may be an appropriate generalization or synthesis, but perhaps more important than the generality itself is the use of certain new concepts and hidden mechanisms. Such new concepts are often referred to as theoretical, as opposed to observational concepts and terms, which refer to objects and properties, directly accessible to the human senses. The path leading from the multitude of astronomical facts to the full Ptolemaic model was not easy. It is not the case that Ptolemy, in a moment of revelation, formulated his theory from scratch, as it were. The development of his conception was influenced by the work of many earlier generations of astronomers and researchers. Their first important hypothesis was that the Earth was spherical. It was supported by a variety of empirical evidence, such as the aforementioned dependence of the elevation of Polaris above the horizon on the position of the observer on Earth. An alternative model of the Earth as a flat disk covered by a celestial sphere also implies certain dependence of that kind, but not to the extent observed, e.g., there would be no position in which Polaris is seemingly on the horizon. In addition, we have the argument from lunar eclipses, which is mentioned by Aristotle. Assuming that the darkening of the moon's face is caused by the Earth's casting a shadow, the circular shape of this darkening unambiguously indicates the spherical shape of the Earth. It is worth noting that the sphericity hypothesis was not only qualitative, but also quantitative. Eratosthenes' famous measurements allowed him to estimate the length of the Earth's radius, surprisingly close to the currently known value. The first astronomical model reflecting the thesis of the sphericity of the Earth was the so-called model of two spheres, the Earth's sphere and the sphere of celestial bodies surrounding it at a distance. However, this model was unable to explain the relative motions of the planets, the Sun and the stars. It was therefore quickly replaced by Eudoxus's model assuming many misaligned spheres, performing independent rotations. Each planet, and also the Sun, was to be attached to its own sphere, which in turn was affixed to the sphere of fixed stars, which made a full rotation in 24 hours. Thus, the movements of the individual planets and the Sun were a combination of the rotation of the fixed stars and the rotation of the individual spheres. Such an otherwise very ingenious solution did not reflect the complexity of planetary motions, retrograde motion, global changes in speed and brightness, etc. The formation of Ptolemy's full model was also undoubtedly influenced by extremely subtle methods of estimating the distances from the main celestial bodies, the Moon and the Sun. The naive belief that all celestial bodies are at the same distance from Earth on a single celestial sphere was quickly challenged by geometric arguments. The comparison of the distances between the Earth and the Sun, and the Earth and the Moon was carried out by Aristarchus of Samos. He took into account the situation in which the Moon's phase is the quarter, half moon, that is exactly half of its disk is illuminated by the Sun's rays. This means that the angle between the direction from the observer to the Moon, and the line connecting the Moon to the Sun is a right angle. By then determining the angular separation between the Moon and the Sun, we can calculate the ratio of the sides of the Earth-Moon-Sun right triangle from simple trigonometric relations. Although Aristarchus made a mistake in his measurements, the result he obtained was astonishing to the contemporaries. The distance to the Sun turned out to be almost 20 times greater than the distance to the Moon. The real ratio is 389.2. Aristarchus also estimated the size of the lunar orbit based on observations of the Earth's shadow during a lunar eclipse. Now let us move on to the complete model of Ptolemy, starting with its basic version, and then making the necessary corrections and additions. Ptolemy's basic idea was to use two concepts to describe the motion of the planets and the Sun, the deferent and the epicycle. The deferent of a given planet and the Sun is a circle in the center of which is the Earth. The deferents of individual planets have different sizes. The planet Mercury had the smallest deferent, not counting the Moon, followed by Venus, the Sun and the three outer planets, Mars, Jupiter and Saturn. It was not possible to determine the exact radii of planetary orbits, so the principle of proportionality to the period of the planet's orbit was applied. The epicycle of a given planet is a small circle whose center is on the deferent. A planet that revolves around the Earth participates in two motions, a rotational motion on an epicycle and along a great deferent wheel. The combination of these two motions results in the observed retrograde motions, i.e. periodic retrogressions of the planets. Only the Sun in the Ptolemaic model did not have its epicycle for a simple reason: it does not show the retrograde effect. Of course, it was a huge challenge to match the size of the epicycles, the deferents, and the speed of movement along these circles to the observed astronomical data. However, it turned out to be possible, although extremely difficult. In this way, Ptolemy's model made it possible to replicate the basic characteristics of the observable behavior of the planets. The use of epicycles and deferents had not only a practical, but also a theoretical, and even ideological justification. In Ptolemy's time, it was commonly believed that the sphere of celestial bodies, the so-called supralunar sphere, was an area of perfection, unparalleled on Earth. Perhaps it was a remnant of the religious approach to astronomical phenomena, in which the celestial sphere was identified with the realm of the gods. Since circles are the most perfect geometric figures, celestial bodies should move only in circles. However, the observation does not confirm this belief. The planets perform complex, chaotic movements, which do not resemble a perfect circular orbit. Ptolemy's genius was to notice that the observed movements of the planets could be reproduced by an appropriate combination of two ideal circular motions, which saved the assumption of perfection. Unfortunately, Ptolemy's idea required additional refinements and corrections, which were moving further and further away from the ideal of uniform movements in circles. The basic model relying on deferents and epicycles did not reproduce many of the known empirical facts we mentioned earlier. For example, one challenge was the observed variability in the brightness of the planets, which could not be explained by the movements on the epicycles and deferents. To solve this problem, Ptolemy assumed that the Earth is not exactly in the center of a given deferent, but slightly offside, at a point called the eccentric. He explained the change in the brightness of the planets by changes in their distance from the Earth. The price to pay for this explanation was the added complication of the model. However, this is not the end of the list of fixes and additions. Another problem to be solved was the global variability of the planet's speed, independent of its retrograde motion. Observations show that Jupiter, for example, moves across the sky much slower during periods of lower brightness than when its brightness is high. This effect could be partially explained by the eccentric, since the angular velocity of a planet depends on its distance from the observer, which, as we already know, fluctuates due to the assumed eccentricity of the orbit. However, it turned out that the eccentric effect is too weak to explain the observed speed fluctuations. So we are dealing here with a very important aspect of explanation or prediction in exact sciences, such as astronomy or physics. It is not enough for a theory to have consequences that are qualitatively consistent with empirical data, we also need quantitative agreement. In order to ensure the quantitative accuracy of the predictions of the Ptolemaic model, an additional assumption of the so-called equant was introduced. The equant is a point located exactly on the opposite side of the deferent center in relation to the Earth. It is an abstract point for which it is assumed that the planet's velocity is constant relative to it. In other words, the planet sweeps equal angles with respect to the equant in equal times. This assumption implies that from Earth's perspective, the observed speed of the planet will fluctuate much more strongly than if the orbital velocity were constant. During the period when the planet is closer to the equant, its actual orbital velocity must be reduced to maintain the constancy of its angular velocity relative to the equant. By combining this effect with the effect of variable distance from Earth, we can fit the model to the actually observed behavior. It may be argued, moreover, that the assumption of the equant does not entirely destroy the conviction of the perfection of the uniform motion of the planets. The planets still move uniformly, but not relative to the Earth or the center of the deferent, but relative to the equant. We have two additional facts to explain: the proximity of the inner planets to the Sun, and the frequency of retrograde periods for the outer planets, no more than once a year. Note that the Ptolemaic model does not in any way force these effects. The inner planets, by the mere fact of being closer to the Earth than the Sun, do not have to stick to the Sun, they could move on their deferents completely independently. The same applies to the regularities in the retrograde motion of the outer planets. The epicycles of these planets could make any number of revolutions in a given period. It is not known why this number would be limited by the solar year. So we need some additional explanatory mechanism. Ptolemy made two assumptions, each to explain the corresponding effect. For the inner planets, he introduced the hypothesis that the center of their epicycles should always stay on the line connecting the Earth with the Sun. With this assumption, Mercury and Venus will be able to move away from the Sun at most by the distance of the radius of their epicycle. The problem of the outer planets was solved by accepting the postulate that the radius of the epicycle of each planet must be parallel to the radius connecting the Earth with the Sun. Then for one full rotation of the Sun around the Earth, there is one revolution of the epicycle, and therefore also one retrograde cycle. Summing up, we can observe that the Ptolemaic model consists of several independent postulates. The fundamental assumption regarding the circular motions of the celestial bodies around the Earth is supplemented by various auxiliary hypotheses. Each of these hypotheses is formulated in order to explain a separate phenomenon. A conjecture posited exclusively for the purpose of explaining one phenomenon is called ad hoc, literally, to that. It is commonly believed that the presence of ad hoc postulates and explanations in science is a sign of weakness of a given theory. Good theories should avoid manual introductions of assumptions just to make them right. The ideal of science is the search for universal laws and propositions that should be able to explain a series of independent facts. One may ask why we should prefer theories based on a small number of independent hypotheses, with a wider range of applicability. Certainly, the elusive issues of elegance, simplicity, or aesthetics in general play a role here. A multitude of hypotheses, each of which has little explanatory power limited to a narrow type of phenomena, gives the impression of chaos and disorder, as opposed to a single hypothesis explaining a whole range of different phenomena. However, there is also an argument referring to the main goal of science, which is the pursuit of truth. Hypotheses in science are evaluated in terms of their probability, or how high the chance is that they accurately reflect reality. From elementary probability calculus, we know that the probability of a joint occurrence of independent events equals the product of their individual probabilities. Thus, if a theory consists of several independent hypotheses, the likelihood that they will be jointly true is equal to the product of their probabilities, and hence will be rather low. A smaller number of independent postulates means that they have a greater chance of being true together. You can find more about the Copernican revolution in astronomy and further scientific developments in the book.